Hi friends, welcome to my channel Path of Physics. Today I am here with the topic Spherical Shell Method. It is an example of radial flow of heat. Using this method we find thermal conductivity of a material. So for that consider two spherical shells of radius r1 and r2. Let them be at temperature θ1 and θ2 respectively. Heat source is placed at the center, so heat flows from inner shell to outer shell. Heat flows along the radius of the spherical shells, so it is called radial flow of heat. Here is what I have drawn here a cross-sectional picture. This is the inner shell. Its radius is r1. It is at temperature θ1. At this point, a heat source is placed. And this is the outer spherical shell. Its radius is r2. It's at temperature θ2. Now, thermal conductivity now the material whose thermal conductivity is to be found is kept in between these two spherical shells. Let its thickness be dr. Its inner temperature is theta and its outer temperature is theta plus d theta. Its radius is r. We need to find first we need to find quantity of heat flowing through the specimen per second. So for that we use law of conduction, equation from law of conduction. Q is equal to Ka times theta minus theta plus d theta by dr times T, where Q is the quantity of heat flowing through the specimen, K is the thermal conductivity, A is area of the specimen, theta minus theta plus d theta by dr is the temperature gradient. Theta minus theta plus d theta is the inner and outer temperature difference. T is the time. Here T is 1 second. So on simplifying this equation we get Q is equal to Ka times minus d theta by dr. Now on rearranging this equation we get Q is equal to minus Ka times d theta by dr. Now in the next step we are going to put the value of area. Here area is 4 pi r square. So we put the value 4 pi r square. Now taking this r square and dr to LHS and bringing this q to RHS, we get the equation like this. And I am integrating on both sides. This on LHS we are integrating from r1 to r2, and on RHS we are integrating from θ1 to θ2. And in the next step on this LHS, this r square is brought to numerator, it becomes r raised to minus 2. This is of the form integral x raised to n dx. Integral x raised to n dx is x raised to n plus 1 by n plus 1. And in here RHS we take out all the constants. Minus 4 pi k by q comes out. And in the next step we are integrating. We get r raised to minus 2 plus 1 by minus 2 plus 1 within the limits r1 to r2. And here minus 4 pi k by q times theta within the limits θ1 to θ2. Integral d theta is theta. And in the next step we get minus 1 by r within the limits r1 to r2, and here we put all the limits. So in the next step we get 1 by r1 minus 1 by r2 equals 4 pi k by q into θ1 minus θ2. On the next step we cross multiply. We do cross multiplication in LHS. We get r2 minus r1 by r1 r2 equals 4 pi k times θ1 minus θ2 by q. Now on the last step we keep k on LHS and bring all other terms on the RHS. We get k is equal to q into r2 minus r1 by 4 pi r1 r2 into θ1 minus θ2. This is the required equation for thermal conductivity. This is the thermal conductivity of the specimen we have kept in between the two spherical shells. This is the thermal conductivity of this material of thickness dr. So that's all for today. If there are any mistakes or you have any doubts, you can comment on it. So thank you.